All right, so we ran out of time today in class, and I just wanted to make sure that we had a chance to go through these last couple questions/problems. So I think where we got to was this question about the soap bubbles, and that's where we had to stop. Okay, so the idea is they're asking what are the three smallest thicknesses of a soap bubble that produce constructive interference for red light with a wavelength of 650 nanometers. All right, so let's think about the soap bubble again. So soap bubble is essentially a layer of water with air on either side. And if we think about light coming in and bouncing off of the top of the soap bubble, because the index of refraction of the water is higher than the air, this light wave will be shifted by a half a wavelength. There might be some light that goes down into the soap bubble or the water, bounces off of the other layer of air, in which has a lower index of refraction, so that one will experience no change. So essentially what we have, if t was, going to 0, there would be destructive interference of these two waves. That means that the path difference that we need to get them in phase to get constructive interference is going to have to be m plus 1/2 times lambda n, where, again, remember that lambda n, which is the wavelength that it would have while it was in the soap bubble, would be equal to the wavelength in air divided by the index of refraction of the soap bubble, which we are going to say is 1.33. So those are the conditions for constructive interference. I think this is misleading the way it looks now. So if we had no thickness, or the thickness was approximately 0, it would be destructive interference. And so I should write here that makes our condition for constructive interference. That's what I wrote down right here. Now it says the three smallest thicknesses, and so let's just say this will change into 2nt is equal to m plus 1/2 times lambda. And so we'll look at m equals 0, 1, and 2 for our three smallest thicknesses. So we have 2nt is equal to either lambda over 2, or 3 lambda over 2, or 5 lambda over 2. So those are our first three scenarios where we would have constructive interference. And then we can solve for the thickness, and we get lambda over 4 times 1.33. We get 3 lambda over 4 times 1.33, and 5 lambda over 4 times 1.33. And so using lambda is equal 650 nanometers, we can put that into these expressions, and the thicknesses that I get for the soap bubble are 122 nanometers, 366 nanometers, and 610 nanometers. So that is what we would have for the constructive interference for the red wavelength of light. Part of the question asks about the three smallest thicknesses for destructive interference. So again, let's just remind ourselves, here's the water, air, and air. We found that this one underwent a phase change, but this one did have no change. And so as the thickness was 0, you would have destructive interference. So that actually gives us our first three smallest thickness. T smallest is 0, because if the as the soap bubble becomes really, really thin, you have inherently destructive interference. The condition to maintain the destructive interference is going to be 2T is equal to m lambda n, because basically you want that difference in the path length to be equal to some multiple of a wavelength to keep it out of phase. And we could have said m would be equal to 0, 1, and 2 here, and then t would be equal to m lambda over 2n. And so our first thickness is 0. Our next one is lambda over 2n. And our next one is going to be 2 lambda over 2n. And so we would get equal to 0, thickness equal to 0. This would be 650 over 2 times 1.33. And then actually 650 over 1.33. And those three thicknesses end up to be 0, 244, and 488. Right? Okay. Our last question, I think, that we have to do is we have a thin layer of turpentine is on top of a sheet of ice. So we have the turpentine, and n is equal to 1.472, and then ice, n is equal to 1.309. We have the light coming down has a wavelength of 400 nanometers, and we want to know what the thickness will maximize the brightness of this reflected light. So we are looking for constructive interference. The light that bounces off of the top of the turpentine will experience a phase change, but the light that bounces off the top of the ice does not. And so we want to have constructive interference. We need the difference in the path length to be equal to some half wavelength, but we want it to be, because we have to get them back into phase with each other. This is lambda sub n. So our thicknesses, so this is going to be with m equals 0, 1, 2, etc. So essentially, I find it easier to write this as 2nt is equal to lambda over 2, 3 lambda over 2, and 5 lambda over 2. And this means that the thickness is going to be, oh, I made a mistake here. This is actually lambda sub n, because the 400 nanometers was the wavelength in the turpentine. So that means that I actually don't need to put the n right here. And so then our thicknesses end up to be lambda over 4, 3 lambda over 4, and 5 lambda over 4. Again, the reason is that they actually gave us the wavelength in turpentine. So they already divided by the index of refraction to get that wavelength. So if I let lambda be equal to 400, I get a thickness of 100, 300, and 500 were my first three. And I see that's already, the 500 exceeds the maximum that I see here, but I see that my answer could have been 100 or 300, and so because it's those two, I would choose more than one above. And oh, I forgot. This was something I wanted to go over from class. What was a Tophat question? And so this was the idea of this wedge of air, but I was asking what would be, basically what would we see here? And the idea is that we have one wavelength bounce off the top of the air and the other one off the bottom of the air. The one that bounces off the bottom of the air had no change, and this one had a half a wavelength of shift. And so basically, as t goes to 0, these two are going to have destructive interference. And that's essentially what we're seeing, or we being asked about, like right where they touch, you know, that's where the thickness of air goes to 0, and they will destructively interfere, and that means we would have a dark fringe at that location. I just wanted to go over that question because there wasn't a lot of agreement when I looked at the Tophat results.